Usually when we think about revolutions, we we kind of picture them happening in sequence, right?
Yeah, exactly, like one after the other.
Right. You have the Industrial Revolution, we all adapt, and then, decades later, you get the Digital Revolution. But right now, based on this stack of, frankly, fascinating new data we've got, we are sitting right in the middle of this massive, invisible infrastructure shift. Two monumental revolutions are happening at the exact same time.
It's pretty unprecedented, yeah.
It really is. I mean, we are electrifying how we move with these continent-spanning commercial EV fleets, and at the same time, we're electrifying how we think thanks to the rapid rise of AI agents.
Mhm.
And for you, the listener, the wildest part of all of this is that both of these forces are completely redesigning the physical world and the actual power grid you rely on every single day,
It is a profound collision, and, well, because so much of it happens completely behind the scenes.
like in data centers and stuff.
Exactly, inside data centers or at commercial charging depots. So it's reshaping our physical reality in ways that most people just haven't grasped yet. To really understand the sheer scale of what we are suddenly plugging into the wall, we really need to look at how the International Energy Agency, the IEA, is framing this.
Right, in their new report.
Yes, the newly released Electricity 2026 report. They have officially declared that we have officially entered what they call the age of electricity.
Okay, let's unpack this because, Age of Electricity sounds like a history textbook chapter from, like, the 1920s, not
Yeah.
2026. What makes right now so fundamentally different?
Well, it comes down to a really specific and honestly quite startling decoupling.
Decoupling. What do you mean by that?
So for the first time in 3 decades, if you exclude periods of major global crisis or economic disruption, global electricity demand is now actually outpacing global economic growth.
Wait, really? I'm struggling to picture that, to be honest.
Mhm.
Usually, you'd think those two lines would move in tandem.
Right, like they're locked together.
Yeah. The economy grows by 2%, we build a few more factories, and so we use 2% more power.
That is exactly how it used to work.
Yeah.
But looking ahead through 2030, the IEA projects electricity consumption is going to grow at least 2.5 times as fast as overall energy demand.
Wow.
Yeah, we are demanding power at a rate that is just accelerating way faster than our traditional economic output. We're using dramatically more electricity just to generate the exact same dollar of GDP.
Okay, so if the infrastructure is already feeling that squeeze, we need to look at what's actually draining the power. Which brings us right into the first revolution, the physical one.
The shift to commercial EV fleets.
Exactly. The sources we're looking at today reveal some really serious hidden growing pains of actually keeping these fleets moving. Like, let's look at the operational data from InCharge Energy.
Right, they've been doing massive rollouts.
Yeah, they've already installed over 20,000 chargers across North America alone. And we aren't talking about, a level 2 charger in someone's garage for their daily commute. We're talking about serving logistical backbone fleets. FedEx, UPS, Cisco.
The massive delivery networks.
Exactly. And they are doing it through this model called charging as a service, or CASHA.
Which is such a necessary evolution, honestly, because deploying EV infrastructure at that kind of scale is highly complex.
Right.
CARIS essentially means a fleet operator doesn't have to suddenly become an expert in high-voltage electrical engineering.
Wait, how does that actually work in practice, though? If I'm managing a fleet of 100 delivery vans, I don't just, buy the chargers outright.
I mean, you can, but it requires an enormous upfront capital expenditure. With the charging as a service model, the fleet pays a predictable monthly operating fee instead.
Oh, gotcha. Like a subscription.
Essentially, yes. InCharge Energy handles the site design. They coordinate with the local utility company to pull those really heavy power lines. They install all the hardware, and crucially, they provide the software to manage it all.
So it completely shifts the burden.
Right. It takes the burden of infrastructure away from the delivery company so they can just do what they do best, focus on delivering packages.
That makes a lot of sense, especially when you look at that Altura Associates case study we have.
Oh, that one is fascinating.
Yeah, they managed the rollout of EV chargers for a major international retailer across more than 500 franchise locations nationwide.
And initially, that was just for corporate social responsibility, right?
Exactly, that and trying to attract a new generation of EV-driving consumers.
Yeah.
But the business results they reported were just staggering. One franchise location literally saw a 60% increase in sales in a single month.
Just from the chargers.
Just by adding those chargers to their parking lot.
Yeah.
And another single retail location made over $3,000 in its first year strictly from the charging fees they collected.
It completely transformed the consumer behavior at those locations. The chargers essentially became this uh, dual-purpose asset, a
Okay.
direct revenue stream, and a massive foot traffic driver.
Yeah, the case study even noted that employees were literally taking snacks and beverages out to drivers while they waited in their cars.
That's amazing. They turned a totally mundane pit stop into this high-touch customer
I
experience.
really love that image. But I am going to push back here for a second.
Sure, go ahead.
Because the Altura report wasn't just a celebration of sales bumps and happy customers buying snacks. There was a section on greenhouse gas analysis that literally stopped me in my tracks.
Ah, the well-to-wheel data.
Yeah. I mean, wait, if the entire point of electrifying fleets and installing these chargers is saving the planet, why did Altura conclude that EVs can actually have a worse environmental impact than gas cars in certain scenarios?
That is the critical nuance of this physical revolution. You see, Altura didn't just measure tailpipe emissions. They conducted what is called a well-to-wheel greenhouse gas emissions model.
Okay, so for those of us who aren't environmental scientists, what does well-to-wheel actually measure?
Think of it as the entire life cycle of the energy. A standard tailpipe measurement only looks at what comes out of the car while it's actually driving.
Right, just the exhaust.
Exactly. But a well-to-wheel analysis traces the energy all the way back to its original source, the well. So for a gas car, it measures the emissions from extracting the crude oil, refining it into gasoline, trucking it to the gas station, and then burning it in the engine.
Okay, so it tracks the whole journey.
Yes. And for an electric vehicle, it measures the emissions from generating the electricity at the power plant,
Yeah.
transmitting it over the power lines, and then storing it in the battery to spin the motor.
Okay, so they are putting both vehicles on a completely even playing field.
Precisely. They looked at 7 different commercial vehicle types using this model. And what they found is that if you plug an electric vehicle into a local electric grid that is dirty, meaning the local utility relies heavily on burning coal to generate its electricity, you aren't actually eliminating emissions at all.
You're just moving them.
Yes, you are simply shifting the emissions from the tailpipe of the delivery van to the smokestack of the coal plant.
So an EV in a coal-heavy region is essentially just a coal-powered car.
In terms of its total carbon footprint, yes. And because there's energy loss during the transmission over the power lines and during the charging process, in the most coal-dependent regions, the overall emissions can sometimes exceed a highly efficient hybrid gas vehicle,
Wow.
which is why Altura stressed that a nationwide rollout needs to be geographically strategic. To actually lessen the environmental impact, you have to prioritize installing these chargers in regions with cleaner, renewable, heavy electric grids. Geography fundamentally dictates the environmental success of the EV transition.
It really highlights how uneven this transition is. I mean, it's like we are trying to build gas stations while the cars are already on the highway, and occasionally they're just running out of gas.
That's a perfect analogy.
The fixed infrastructure is just struggling to keep pace with the sheer volume of vehicles hitting the road. And nothing proves that better than the operational data from B-Charged EV.
They've seen incredible growth.
Yeah, they have become America's #1 emergency mobile charging company. Their data shows they powered 250 fleet vehicles in just 60 days across 15 different states.
And we should probably clarify what mobile charging actually means in this context.
Right. They aren't like towing these vans. They are literally deploying massive batteries mounted on trucks or trailers, driving out to fleets that are stranded because the permanent infrastructure either isn't built yet
Ah.
or the local grid failed, and they are charging them right out in the field.
Which highlights a tremendous vulnerability in the system. We are electrifying physical labor and complex delivery networks at lightning speed, but the physical foundation beneath it is still playing catch-up.
Now, if local infrastructure is buckling under the weight of commercial EV fleets, what happens when we start stacking unprecedented digital demands on top of it? This brings us to the second revolution. Just as we are electrifying manual labor, we are simultaneously electrifying cognitive labor.
Exactly. We are transitioning from the physical energy drain to the digital energy drain. And to understand this, we really have to look at the maturation of artificial intelligence in the workplace.
Yeah, the latest Microsoft 2026 Work Trend Index data on this is wild. A staggering 88% of organizations are now regularly using AI in at least one business function.
It's everywhere now.
It has completely saturated the enterprise landscape. But it's not just that they are using it, it's how they are using it.
That is the key distinction. We have moved far, far beyond the initial wave of simple chatbots, where you type a prompt and a large language model spits back a paragraph of text.
Right.
The Microsoft data shows that 62% of companies are now experimenting with AI agents, and 23% are actively scaling them across their entire enterprise.
Here's where it gets really interesting. If a standard AI model is like a really smart calculator that gives you an answer, an AI agent is like hiring a digital intern.
I like that comparison.
Yeah, they actually execute multi-step workflows. You don't just ask them a question, you give them an objective. You say, analyze these 100 vendor contracts, flag the non-compliant clauses, draft emails to the vendors asking for revisions, and then put the responses into a spreadsheet.
And the agent plans the steps and acts in the real world.
Exactly.
And the data shows that high-performing companies are not just using these digital interns to cut basic operational costs, they're using them to fundamentally redesign their workflows and drive top-line growth. But, this raises an important question.
What's that?
What happens to the human workforce when digital interns start executing complex workflows at scale?
Right. The Microsoft survey highlights a very real workforce anxiety. Around 32% of respondents expect a decrease in their overall workforce size in the coming year due to AI adoption.
But look at the counter trend in the exact same report.
Yeah.
At the exact same time, there's a massive hiring boom happening for data engineers, software engineers, and roles related to machine learning operations. It's a total rebalancing of required skills.
Companies are shedding administrative roles and just hoarding computational talent,
Precisely.
which slams the digital revolution right back into the physical world.
I think there is a huge misconception that AI just exists in the cloud, and the cloud is just this invisible, magical space. But the cloud is just a building full of computers, right?
Exactly. Where do these AI agents live? They live in what are called hyperscale data centers.
What makes a data center hyperscale? It comes down to the architecture and the sheer density of the computing power. Traditional data centers were built for internet traffic and standard racks of standard processors or CPUs.
Right.
But AI requires a totally different kind of math. Every time an AI agent executes one of those complex multi-step reasoning tasks you mentioned, it requires specialized chips called GPUs running at absolute maximum capacity.
And those run hot, don't they?
Incredibly hot. So a hyperscale data center isn't just a warehouse of computers. It is an industrial-scale thermal management facility. They require intensive water cooling systems and immense electrical power just to keep the servers from melting, let alone doing the actual computing.
Wow. So an AI agent reasoning through a complex task consumes fundamentally more physical electricity than a standard internet search.
Exponentially more.
And this is where the two revolutions collide. You have Microsoft's AI agents scaling up globally in these hyperscale data centers. And you have InCharge Energy's 20,000 EV chargers pulling high voltage across North America. Both of these incredible innovations are on a collision course over a single finite resource, electricity.
And that bottleneck is exactly what the IEA Electricity 2026 report warns us about.
Yeah.
They outline that electricity demand in advanced economies, places like the US and the European Union, is accelerating again after 15 years of total stagnation.
15 years.
Yeah, for a decade and a half, demand was completely flat due to energy efficiency gains. Now, because of the combined weight of data centers, AI, and EVs, it is surging.
The numbers in the IEA report are genuinely hard to wrap your head around. Global demand is forecast to rise by 3.6% annually through 2030. To put that in perspective, the report notes that over the next 5 years, China alone is expected to add new electricity demand that is equivalent to the entire current electricity consumption of the European Union today.
It's staggering.
China is building an entire Europe's worth of power demand in just 5 years.
The sheer physics of that growth is totally unprecedented.
So I have to ask the obvious question. Are we literally going to run out of power? Can the grid actually handle millions of new delivery vans and an invisible army of AI digital interns operating 247?
Well, generating the power itself is not necessarily the core problem. The real crisis is in transmission. The IEA reveals a truly shocking statistic. There are currently 2,500 gigawatts worth of projects. This includes new renewable generation, storage, and data centers that are stuck in grid connection queues worldwide.
Hold on, I need to visualize that. What does a gigawatt actually power?
Roughly speaking, 1 gigawatt of electricity is enough to power a mid-sized city, or about 750,000 homes.
So 2,500 gigawatts is like the power equivalent of 2,500 cities just stuck in a line waiting to be plugged in. How does a power project get stuck?
Think of the electrical grid like a city's plumbing system.
Ah.
You can build the biggest, most advanced water tower in the world, that's your new power plant or solar farm.
Okay.
But if the pipes leading from that water tower to the houses are only an inch wide, it doesn't matter how much water you have, the pressure will just burst the system.
Oh, I see.
Our transmission lines are those pipes. The grid is heavily congested. Getting a new project connected requires navigating years of bureaucratic permitting, local zoning laws, and waiting for utilities to physically upgrade the high-voltage transmission lines to handle the new load. The power generation is there, the demand is there, but the physical wires connecting them are the bottleneck.
Okay, so if we can't just lay millions of miles of new copper wire overnight, how do we adapt? The whole system can't just grind to a halt.
It isn't, but the solutions require immense ingenuity. The IEA report highlights that meeting this demand requires investing heavily in what are called grid-enhancing technologies, or GETs.
What does that mean in practice?
It means using hardware and software to squeeze more capacity out of the wires we already have. For example, deploying dynamic line rating sensors on existing power lines to monitor temperature and wind in real time.
And what did that do?
It allows grid operators to safely push more power through them than older static models allowed. It also requires deploying massive utility-scale batteries to store power.
Are we talking about giant lithium-ion batteries like the one in my phone, just scaled up to the size of a building? Because mining enough lithium to power an entire grid seems physically impossible.
Lithium-ion is a major part of it right now, yes. But at the utility scale, we are also seeing rapid deployment of alternative chemistries, like iron-air batteries, which use abundant materials to store energy for much longer durations.
Oh, interesting.
Yeah, the goal is to store power when demand is low, say the middle of the night, and discharge it during peak hours to relieve pressure on the transmission lines. But the most immediate solution, and the cheapest, is utilizing advanced software.
Which ties perfectly back to what InCharge Energy is doing with their fleet chargers. They have this software called In Control. And what it does is smart load management.
Exactly. This is where the digital solves the physical.
Right, because when a driver plugs in a massive FedEx van, the software doesn't just pull maximum power instantly. The software's API communicates with the local utility's pricing grid millisecond by millisecond. It reads the grid's stress levels.
Right, it's constantly adjusting.
Yeah, if it's 5 p.m. and everyone in the city is turning on their air conditioning, the software throttles the charging speed down. By automatically shifting the bulk of the charging to midnight, when the grid isn't stressed and wholesale power is cheap, InCharge's data shows these fleets are saving an average of 45% in electricity costs.
It's incredible.
They're basically using code to physically maneuver around the limitations of the grid.
And that kind of software flexibility is going to be paramount, especially as the makeup of the grid itself fundamentally changes. Because the final major piece of the IEA's forecast is that renewables and nuclear power are set to generate 50% of the world's global electricity by 2030.
Half the world's power from renewables and nuclear in just a few years? That's a massive shift from fossil fuels.
It is. Solar PV is generating record amounts of electricity globally. Nuclear power is hitting new records with reactor restarts in Japan, higher generation output in France, and huge new capacity coming online in China and India.
Right.
But think about what that means for grid stability. We are moving away from highly predictable baseload power, where you can just burn more coal or gas exactly when you need it, to highly variable generation like wind and solar, supplemented by nuclear.
Which makes that in-control software absolutely vital. If the wind happens to blow really hard at 2 a.m. when human demand is low, the grid needs the software to instantly tell thousands of EV fleets to wake up and charge at that exact moment to soak up the excess power.
Precisely. You cannot separate the digital software from the physical hardware anymore. They are a deeply interconnected ecosystem.
And that is exactly why this deep dive matters so deeply to you, the listener. Whether you are managing a business logistics network, whether you are trying to navigate a workplace that is suddenly integrating autonomous AI agents, or honestly, if you are just sitting at home turning on your air conditioning during a heat wave, your daily life is becoming physically entangled in this new age of electricity.
The foundational infrastructure that supports the modern economy is being completely rewritten in real time.
So what does this all mean?
Well, it means that true success in 2026 and beyond isn't just about adopting the coolest new AI software, and it isn't just about buying a shiny new electric fleet to hit a corporate sustainability goal. Success requires understanding the invisible physical infrastructure that makes those technologies possible in the first place. You have to understand the grid.
It all comes back to the plug. We started by looking at two massive revolutions, electrifying how we move and electrifying how we think. But they are entirely dependent on the physical capacity of our energy networks, which leaves us with a final thought to ponder as you go about your day.
And what's that?
If our physical grid ultimately dictates the speed of our digital innovation, will the next great tech monopoly be a software company? Or will it be the company that figures out how to transmit the most electricity?